This video is going to be about phase diagrams. A phase diagram looks like this. On the y-axis, we have pressure, and on the x-axis, we have temperature. So at high temperature and low pressure, we're in the gas state. At low temperature and high pressure, we have solid, and in between here is where you have a liquid. So if you go across this line, from solid to liquid, you're melting, also known as fusion. Backwards is freezing. Going from a liquid to a gas, vaporization. Backwards is condensation. Going straight from solid to gas is sublimation. And the reverse is deposition. So these are all the phase changes that we've been looking at all semester. There are some other features here. You have a triple point right here, which is the temperature and pressure, that you have all three phases, a solid, liquid, and a gas. And then we have this critical point up here, which we'll talk further about. There are some different factors affecting the physical states. First, we have intermolecular forces, which we've just talked about. We have the strength of attractive forces compared to the kinetic energy of atoms and molecules. The temperature, which affects the kinetic energy of atoms and molecules, and the pressure, which affects the distance between atoms and molecules. For the physical state and phase transformations. So a phase diagram is a graphical representation of how the stabilities of the physical states of a substance depend on temperature and pressure. The equilibrium lines represent phase changes between solid liquid, liquid gas, and solid gas under specific conditions or different temperature and pressures. The supercritical region is the fourth state of matter with properties intermediate between gas and liquid. So here, these are the equilibrium lines. So where you have those phase transitions between solid, liquid, and gas, those are called equilibrium lines. And then up here is the supercritical region. So anything above the critical point is going to be a supercritical fluid. Some features of phase diagrams. The triple point is the temperature and pressure where all three phases of a substance coexist. The critical point is a specific temperature and pressure at which the liquid and gas phases have the same density. And the supercritical fluid is a substance above its critical temperature and pressure. Liquid and vapor are indistinguishable. The triple point is here, and that's where you have liquid, solid, and gas all coexisting. And then the critical point is over here, and above the critical point you have supercritical fluid, where the liquid and the vapor are indistinguishable. So let's look at the phase diagram of water. So every different compound is going to have its own phase diagram. So over here we have solid ice, liquid water in here, and gas in here. So one skill I would want you to have is to be able to look at a blank one and label where the solid, where the liquid, and where the gas would be. So I want you to recall, if you look in this corner down here, when we talked about heating curves of water, and remember we talked about the energy required to turn it from a solid to get it up to the melting point, and then the energy for the phase transition, and then heating again to heat the liquid, and then all the energy you have to put in for that phase transition to turn it into a gas, and then heating. So if we look, this is happening at 1 atmosphere. So if we go over here to the phase diagram at 1 atmosphere, so this line right here in the green region, that corresponds to this area here where we're heating it. Then the melting is what's happening when we cross this equilibrium line. Then the liquid is when we're heating the liquid. And then right at that line, that's the boiling point. So that's where we're undergoing that liquid to gas phase. And then as we keep heating, that's when we're in our gas region. So it's basically like a whole bunch of these plots put together for different pressures. And that all comes together to be the phase diagram. So I do want to note something about the water phase diagram compared to the carbon dioxide, which is here on the right, and most other substances. So I want you to take a look at the curvature of the blue line. So that's this one right here. And see how for water it kind of goes backwards right here? So for most compounds, it goes to the right. For carbon dioxide and most other substances, increasing the pressure will make it turn to a solid. So right here, if you keep increasing the pressure, for example, it'll turn into a solid. Whereas for water, if you're right here and you have a solid, you keep increasing the pressure, you can actually turn it into a liquid. So for water, which expands when it freezes, you can see the line is almost vertical with a backward curve at high pressures. So that's very unique of water. Most other substances will have a line that looks like this. So there are some important repercussions since water expands when it freezes. The density of water actually decreases as it freezes. So most things, when they turn into a solid, the density increases. So most solids will sink. But water, you've all seen ice cubes and you know that they float in liquid water, and that's very unusual. And the reason is, we just learned about hydrogen bonding, and it results in a cage-like structure in a solid state. So it's less dense than liquid. So it forms this kind of cage structure, which means you have a little bit more air, a little bit more space, so it's slightly less dense. So here's the temperature. This is from 0 to 10 degrees Celsius. And you can see these densities are all very close to each other. But if we look right here at 4 degrees Celsius, liquid it's at its most dense. And then if you keep cooling it, it actually becomes less dense. And that's why ice cubes float rather than sink. So this is relevant in real life for aquatic life. So you probably all, you know that some lakes and rivers will freeze, and they freeze from the top down. So the solid floats on liquid, unlike most substances, which allows fish and aquatic life to survive below. So imagine if it froze from the bottom, it would freeze completely solid and all the fish would die during the winter. As the surface waters warm or cool, nutrient-rich bottom waters cycle to the surface, and oxygen-rich surface waters cycle to the bottom. So as that temperature slightly changes, the density changes a little bit, and it'll sink or rise depending on the temperature, which will help circulate nutrients and oxygen throughout the water so that aquatic life can stay alive. So let's do kind of a little practice problem of what we might see with a phase diagram. I want you to describe the phase changes that occur when the temperature of carbon dioxide is increased from negative 100 degrees Celsius to 60 degrees Celsius at a pressure of 10 atmospheres. So if you look at the temperature scale, you can see it goes from negative 100 to 60. So we want to see what's going to happen on this entire scale. And we're looking at a pressure of 10 atmosphere. So let's put a line across here for our 10 atmosphere. And we're going to follow this line and see what happens. So at negative 100 degrees Celsius, we're in the solid state. As we keep traveling along this line, we're going to see right here is where melting is going to occur. And that's about negative 56 Celsius. Then we'll keep traveling along this line till we hit this red equilibrium line. And then we'll look down here and say that that's about negative 38 degrees Celsius. And that's when we're going from liquid to a gas. Then it's going to be a gas all the way until 60 degrees Celsius. So this bottom part here is kind of what you would describe for a problem like this. So go ahead and practice looking at phase diagrams. Make sure you can label them to know where the liquid, gas, and solid goes and where the triple point, critical point, and that supercritical fluid are. So just be able to get used to reading them, looking at them, and interpreting them.